All right, and it seems like we are live. So, hello everyone, and great to see you again for this month's edition of the Rookie Rules discussion. It's my great pleasure to introduce Remo from the Max Planck Institute for Astronomy. He's going to tell us about between steam and stone, the role of volatile delivery, phase, and partitioning in settling planetary radii. Now, as a reminder of netiquette, please, while you're in this Zoom room, use your full name, keep yourself muted throughout the talk, and during the question session, please turn on your video whenever possible when asked questions at the end. The talk will be between 30 and 40 minutes, and after that, there will be plenty of opportunity for all of you to ask your questions. So yeah, without further ado, I will stop sharing my screen, and Remo, you can start sharing yours, and then take it away.
Thank you very much, Rob, and thank you for the invitation here. I'm happy to talk to you about volatile partitioning and distribution in the planet and how this affects planetary radii. So the talk will be have some introduction slides, so I hope the experts in the audience can bear with me until I come to some newer results at the end. Bottom line here is that I want to show you that sub-Neptunes, the planets above the radius valley, can be water-rich migrated worlds, and that our formation modeling, so I'm doing theory, so this is a theoretical talk, can actually favors this scenario. And in the last part then, I will show how water partitioning to the interior can affect the results. So for this audience, this is probably known that we have a degeneracy. If we only measure the exoplanet mass and radius, we can have the same mass and radius with a planet which has, for example, water ice and rock, or a bigger rocky core and hydrogen helium on top. So we don't know from these measurements. And to complicate things even further, it is possible that water or other volatile species, volatile elements, then partition to the mantle and the core of the planet, the metallic core. When I say core today, I mean the metallic core, mostly iron. So how could we try to break this degeneracy? Is one approach is that instead of looking for the individual planet, trying for the individual planet, checking whether statistical features in the exoplanet demographics can be reproduced by models. And one such feature is the marked in red here, this radius valley. So even though you might not see it on this plot, believe me, it's statistically significant that there's an underdensity here of planets around 2 Earth radii. And another important a feature is this blue triangle. It's the photoevaporative or the sub-Neptune desert. So this is in principle at higher radii than the radius valley, although the mechanism might be linked. This was on the orbital period versus radius plane, but more and more in recent years, we started to characterize exoplanets, the field, and when a mass radius plot, so now masses against radii for planets where we have measured both, it looked like very unpopulated here in the lower mass regime in 2007. One basically only had the solar system planets and one exoplanet here in this regime. Now this has changed. Last year, in the catalog by Lena Park, we have hundreds of planets, even below 100 Earth masses. But it's important to note that these planets do not all orbit solar mass stars, or there's different stellar host stars assigned to them. And now I would like to talk about two mechanisms that are important throughout this talk, and I think also important in shaping the planetary population. One is photoevaporation, and there's of course different regimes of photoevaporation. What I will be talking about is hydrodynamic outflow, so very strong, vigorous mass loss. And in that regime, it's not such a bad approximation to just check the energy balance. So you basically look at energy in, so this pi times some base layer where the XUV high energy radiation is absorbed. So of course you have the flux of the XUV radiation and the surface of the planet, the energy input, and then you check against the gravitational potential plus some factors of order unity, and like that you get an estimate of your mass loss rate. That's approximately the case. And with photoevaporation, it drives then mass loss of the planet. And if you start with a rocky core and just add a little bit of atmosphere on top, so I follow here a very nice paper of Owing from 2019. You then have longer and longer mass loss timescales because your mass loss rate is more or less constant. If the radius doesn't change and the mass doesn't change significantly, you have a constant rate. And the more mass you add, the longer your mass loss timescale. And then at some point, adding more mass or significantly more mass, you actually start to change the radius of the planet. And both the tau equals 2/3 and the base of the absorption radius, they will increase. So this gives you a power 3 dependency on the radius of the planet. And if you add more atmosphere mass, actually the mass loss rate is increasing, and therefore the mass loss timescale goes down until when the gas starts to compress the planet. So adding more gas is then not just increasing the radius, but actually not so much changing the radius anymore, because self-gravity compresses the atmosphere, which is about at 1:1 mass ratio of the atmosphere to the core. And then if you add more mass, you're basically becoming a giant, which has a very long mass loss timescale, because of the large gravitational potential, but also because it's very dense, which is, of course, compact objects. So this gives you two regimes, one just above the terrestrial planets, the pure rocky cores, and another one at the atmospheric mass fractions around 1, where photoevaporation rates are high. And if you then transfer that to an exoplanet statistics picture, that means at those two locations you would have a gap, an M. So this here is the radius valley, and this here is the Neptune desert in this simple picture. And this works really well. But there's a free parameter, which is the mass. So the core mass is often in pure evolution models one can choose, because in one work by Rogers and Owing, it was even retrieved. So they did a retrieval exercise, which is quite cool. My approach here will be to remove this free parameter by coupling the evolution to formation models. So it's more modeling, of course, more model dependent, but you don't have this free parameter of the planetary core mass. And therefore we can test formation evolution, combined formation evolution models against observations. The other key ingredient is migration. We have for a long time expected disk migration to happen. So if planets form in disks, and gas giants have to form in disks, they will also migrate. This is mainly due to, so first order explanation here, very quick, is that if you go to the co-moving frame of the planet, the gas is moving in this diagram to the bottom, outside of the planet, but in the other direction, inside of the planet. And like a boat in water, the planet excites a wake by moving through the gaseous medium. More technically, this is called the Lindblad resonance. And as you can see here in this simulation from 2014, for the typical disk profiles, those two wakes are quite asymmetric, just from the geometry for once. You get different strengths and different torques of those wakes, of those overdensities of the material. They, of course, exert a torque onto the planet. The outer wake is trying to pull back the planet. It's trying to remove angular momentum, while the inner wake is accelerating the planet. And as you can see in this image quite well, the outer wake is for most cases stronger, so the planet loses angular momentum and spirals towards the star. This is type 1 migration, first order. There's other regimes and other effects, such as the corrotation region, and you can go to this review in PP7 if you need to learn more about migration. Also, low viscosities is a very different business again. What it does, so for the viscous case, is summarized here in this map. So this is what we call a migration map. On the bottom left here, we have distance versus planet mass. Blue is inward, red is outward migration. This is using the Particle-Cooper 11, 10, and 11 formulas. And if you have a planet, let's say, starting here, it keeps accreting solids. It's growing up to this red region. Then it moves outwards, and it goes up and right in a numerical simulation. So it follows this white transition line where the two torques balance. And then when the corrotation torque saturates, or in lower viscosity disks, it's similar, but there's no outward migration here. You will migrate rapidly towards the star. The dark blue region here means it's a rapid migration, 100,000 years or faster, and the planet then goes into the inner disk quite quickly. And the blue region here is where we expect water in ice form, so it's outside of the sublimation temperature of water here in the disk, and if a planet accretes solid there, it will be water-rich. This picture can also help to explain several of the inner system architecture trends, the mean motion resonances, for example, but also the non-resonant systems by breaking the chains again. But I would say we have no proof that this is true. We don't have an observational proof. This is a theoretical expectation, especially for large-scale migration. You can also get mean motion resonances if you only migrate over shorter distances. So, coming to my modeling is what is marked in red in this diagram overview of planet formation. So we do planetesimal accretion onto protoplanets or embryos, what we call protoplanets or embryos, which is initially moon mass objects. They can accrete gas or become terrestrial planets. So this slide is more to introduce the nomenclature. And here we have this green line is what I will be also talking about, which is the pebble accretion onto the embryos. In words, we have in this first work I show here today is from last year. We coupled the formation phase from 21, where we used population synthesis approach to new evolution calculations. So the formation part includes planetesimal accretion, disk evolution, migration, as I showed, and n-body interactions of 50 n-body particles, or 100 in the solar mass case. And we solve the vertical structure or the internal structure of each planet, so in one dimension. And this then automatically, by cooling that, gives you a gas accretion rate in the attached phase. We take this structure, these planets, so we keep the structure and move to the evolution phase at some transition time. And the evolution phase is then more efficient computationally because we turn off the n-body interaction. So each planet is evolved independently. And in this evolution phase, photoevaporative mass loss is considered. Actually, sometimes we check against the energy limited regime, but we have more detailed tables of hydrodynamic simulations of hydrogen, helium, and water escape from those atmospheres. And one has to assume an equation of state, which is varied here for the evolution phase. What the formation phase looks like is often good to show a plot to visualize instead of going into all the details. One can see here mass versus distance diagram, and the inner rocky planets in yellow and the water-rich planets in blue growing. So the outer system is now at around 1 million year growing, and the planets in this simulation reach this 10 Earth mass regime, fast migration, and you could see how they perturbed the inner disk they migrated in. There were collisions with the crosses appearing, and in this case we have a system with several sub-Neptunes, migrated water worlds, water-rich planets interior to the ice line. And on the population level, if we repeat simulations like that 1,000 times by varying the initial conditions, we get a population like that. So this is the population synthesis exercise. We get then these blue points, the water-rich planets in the inner disk. They have around 30% of water by mass. And of course, there would be other ices that they can accrete, but often these ice lines are further out. So the planets which are most efficiently grown just outside of the water ice line often have really a lot of water, while the other species are not so common. And this result is in no way new. So this is really classical. Every planet formation simulation, which includes migration, will get this kind of. So this is basically because the type 1 timescale is so short at this mass regime, one gets at least some of these migrated water-rich planets. Depending on the parameters, they're more common or less, but they're really ubiquitous in these kind of modeling. And then we wanted to see whether we match the radius distribution for these planets. And that's the story of this paper from last year. Of course, this was the first calculation that we did. We assumed the planets to be made from rock, rocky core, so rock and iron metallic core, and a water ice layer on top. And this is a high pressure water ice that we assumed. And when you do that, the planets often lose their hydrogen-helium envelope, which is the outermost layer on top of that structure. And then if one fits a radius valley, it is located somewhere between 3 and 4 Earth radii, and not at all where it's observed. It should be at 2 Earth radii. And exactly where the valley should be, you get, if you plot the histogram, you get a peak. So it's exactly wrong. And so one can, of course, then say, okay, planets, water-rich planets don't exist, are not there, but there's another thing that we did wrong, which is we used the wrong phase, basically. If one does that, because the observed exoplanets are hot, especially those around solar mass stars, and they're all inside the runaway greenhouse limit, so water is not expected to be liquid or ice, because as you can see here in the phase diagram, often the planet's even the surface temperature is above the critical point, or even if it's below, the typical interior structure, the further you go in, is then crossing above the critical point, and then the interior of the planet is supercritical. The further the outer layer are then still gaseous. And of course, there's no phase transition here. So you have this supercritical gaseous structure, and the high pressure ice are really orders of magnitude away, almost an order of magnitude in temperature away to reach. With this kind of equation of state or phase for the water, one gets a different result. And we were not the first to notice that there's an issue like that, but it was certainly not common in the field to use supercritical water yet. I think this changed in the recent years. And one more thing is that supercritical fluids are miscible. So one would expect the supercritical water and hydrogen helium to mix, at least in the lower part of the envelope. Even the silicates could be supercritical, but this is a different story which I didn't include yet. So what came out with mixed supercritical water and hydrogen helium atmospheres, let's just call them steam, steam worlds, is then that they are in agreement with observations, more or less, at least the first order. So we have now, if you look here at the radius period diagram again, we have recovered the radius valley. It separates the dry rocky planets from the water-rich sub-Neptunes in that case. The histogram looks even better than if you also include the period. And when we did the Kolmogorov-Smirnov test to check whether the two, the observed and the synthetic distribution are the same, actually for the planets within 30 days orbital period, we cannot exclude that they're drawn from the same. And this is something that theorists usually never get, because it's a theory. It's not a fit to observations. It's a model, and the model is never as good as nature, and that's normal. But so we were really happy with this result, and I think probably won't have such a nice result again in the future. So this was the conclusion slide, basically, that of this project. Not the end of the talk yet. Stay with me. That we can have sub-Neptunes, water-rich sub-Neptunes. We probably need photoevaporation. So in our model, we did not get a clean enough radius valley if we did not include photoevaporation, and condensed water should not be used anyways, and also leads to the wrong distribution. Cannot rule out the dry scenario, of course. But the formation model predicts the other one, the water-rich one. One interesting aspect is also the mass distribution, because as I mentioned before, one does not often have the masses for these, at least not for the whole picture of Kepler planets. And our mass distribution is kind of unimodal if you look at gray, but there's a shift from rocky to water-rich to then planets which also have hydrogen, helium. So if you go from lower to higher masses, there's this shift. The pebble accretion based model by Venturini 2020, she had an effect from pebble accretion that even the mass distribution was bimodal. So this is because if you change the fragmentation velocity of the pebbles, so the size basically of the pebbles at the water ice line, pebble accretion is much more efficient outside the water ice line than inside, and this gives you even from the formation model a bimodal mass distribution, as you can see here. And then it was actually not so clear whether the radius valley was due to this bimodal mass distribution basically from nature, or whether it was an evolutionary effect. And it's interesting that the planetesimal accretion model predicts a different mass distribution than the pebble accretion model. So we thought we might try to test that in the N-course observational paper from Dave Armstrong. But if you also include collisions among the planets, actually a lot of the effect is lost. You can see here in the lighter color that the sub-Neptune, so above gap planets here, of the simulated pebble accretion planet is more flat than the planetesimal accretion one. So we have a difference in the predicted planets, but I would say with the data that we had in this paper, we cannot rule out either of the scenarios yet. But probably with Plato and more data, this will be one of the possible tests. Of course, not everything was perfect last year. If we look at the radius versus period distribution again, we see this blob of blue points here, which is actually not in the observations. We also did not have the right slope of the radius valley. If you look at the numbers here, not exactly at least. And one issue was that there's planets that keep their pure water envelope. So from formation, we initialized them in the evolution phase with pure water because when we did the transition, we did that after 100 million years of N-body evolution. Planets could lose their hydrogen, helium in the formation phase, but we assumed in the formation phase that the water is still below the hydrogen helium, so it couldn't be lost. And I think this is not a good, this is not the right way to do that. We expect that water and hydrogen helium would also mix early during formation. So to mimic that a bit, in my recent submission to archive, well, not just to archive, also to A&A, but you can find it on archive already. We use the hydrogen helium mass immediately at the end of the disk stage for the mixed scenario. So the mixed scenario is basically same as before, as what I talked about before, but we changed this. We added more hydrogen helium basically to most of the planets by just looking in the history of the formation model at how much hydrogen helium it had at the end of the disk stage. We also checked whether what happens if hydrogen helium and supercritical water do not mix. That is this layered scenario, so not assuming condensed water, but just not mixing them. Then we had a fractionation test. So if the photoevaporative mass loss could fractionate water from hydrogen. So fractionation means water is staying behind while the hydrogen is lost. And the last thing we tested was a first attempt at interior atmosphere coupling using the models of Caroline Dorner and her group. So she predicts that material can also dissolve in the metallic core, in the iron core. So water in our case, we use that for water. Water can be dissolved in the iron core, and we assume that there's always a magma ocean present. So this is it's molten rock, which can take up much more water than solid rock. So we kind of make the maximum. We use kind of the maximum of water that we can sequester into the interior and try how much this affects our results. So for the mixed model, similar to the works before, we actually have not a bad fit. I would say it's a kind of a good fit to the catalog by Lena Park on mass radius. Of course, this catalog is not a homogeneous survey, so we cannot do rigorous statistical testing. So qualitatively, it looks relatively good. We wanted to look at this issue with the desert, of course, I mentioned before. This now looks like that. So there's more of there's no longer a blob there, so it's more a clean line. Of course, there's no pure water planets anymore because we added hydrogen helium to all of them. Oh, sorry, initialization. But I think you probably are right if you point out that this is still not a good match in period. So maybe we would have needed more hydrogen helium, but there's anyways probably from the formation model, this underdensity here of planets where there's most of the sub-Neptunes in the observations has probably something to do with the formation modeling already. So might be some kind of stopping radius for the planets or something like that. So we're still trying to figure that out. The slope changed a bit, so it's closer to the observed one, and also the location of the gap is in better agreement than before. One can also try to fit the mass radius relations. I think this is relatively insightful for the models because you can have these points at the highest rocky planet mass might tell you something about how massive the rocky planets can form. The lowest sub-Neptune mass might be informative in telling you what is the planet mass which can still retain an envelope, and then the slope of the sub-Neptunes should also tell you something about the material which is lost or the strength of photoevaporation. So I think this is a useful analysis, but we didn't have a great match with observations yet, with a basically a bit too shallow sub-Neptune mass radius relationship. Here I also show you this layered model test where we have an accumulation of sub-Neptunes. We have more sub-Neptunes, more keep their envelope because they first lose the hydrogen helium and then have a dense water envelope which remains. And I don't think this is in better agreement with observations. And for fractionation, I expected an effect, so that's why I I started this exploration. But we see nothing. Basically, on population level, and even for the individual planets, the changes are really small. And this is because fractionation of a water from hydrogen or any mass fractionation is only happening if the escape rate is relatively small. So if you only remove some of the top of the planet, while if you drive a more hydrodynamic flow, so if you drive a lot of mass loss, the gas is coupled relatively well. So you have higher densities. You lose also the water while when the hydrogen escapes. So because we start always with massive envelopes. So we took them right after the disk stage. We transformed the water into the envelope. They all have massive envelopes. Um, we if the planet is in the regime when it has only little mass loss and therefore would have fractionation, there's so much envelope mass that it never changes the bulk of the envelope. While if it loses its envelope efficiently, we're always in the regime where there's no fractionation. So I don't think we have something which is in disagreement with previous works who found an effect of fractionation. It's just our initial condition is different. So we don't have below 1% masses, envelope masses, but we have something like 20-30% of the planet mass envelopes. And therefore, we don't, which this is again a prediction from the formation model, we don't predict that we have deuterium or helium enriched sub-Neptunes or even fractionation of water. So this is something which we don't expect. So a negative result, but I think it's also worth reporting. Then for the water sequestration, the story is a bit similar to this layered scenario. You have less water in the envelope because you put a significant amount, it's really a lot of the water goes into the core and mantle. And then the planet increases in size. Remember about the self-contraction, the planets are in this regime. We are then in the regime where there's more vigorous mass loss often, and you have more efficient stripping of the planet. And then only by outgassing, where we assume that there's an equilibrium between the envelope and the interior always established after each time step, only by outgassing you then get more and more into a smaller, more water-enriched envelope. And then the results look accordingly. We have this blob here of planets which have higher metallicity envelopes, so enriched water-enriched envelopes. They move down there efficiently and then stay in this regime. I don't think this overdensity is as strongly observed. So I would say it's not in better agreement with observations, but it's also not ruled out that something like that is happening, at least in this 10 Earth mass regime. Maybe it's a stretch to extend these assumptions down to 2 Earth masses. So maybe that is what is going on. And if we put these results in the same plot here, we see that yeah, indeed the sub-Neptune mass radius relation lies below the mix and the fractionation model and relatively close to this layered scenario. So basically has a similar effect as if you would layer the water below the hydrogen helium. Note, these results are not the same as in the archive because I discovered a bug in the sequestration model. Basically, this equilibration, this outgassing didn't work in what is on the archive. So if you want to see how it looks like without outgassing, you can directly go to the archive. If you need those equilibrium outgassing results, you have to wait for a few weeks. Another thing, because here we varied also in this work we also varied the stellar mass. We can look at the trend that was discovered by Julia last year, that the lower the stellar mass, the more the lower mass the sub-Neptunes or the planets above the valley, at least they are above the density valley, right? As you can see here. So if you look at just radius, you would see that the valley is more and more populated, the radius valley is more and more populated from above, while a density valley persists. It's just a diagonal in this diagram, but the radius valley is filled from the top with sub-Neptunes. And this is because the sub-Neptunes or the water-rich planets migrate at lower mass around lower stellar mass. That's the main reason. So it's from formation. But to see the effect, it's also important. So we see it, but weaker to a lesser degree in our simulations as well. But it's really sensitive to your orbital period cut, because if you're in a regime where photoevaporation also removes water-rich envelopes, you lose the effect. So you lose the planets above the density gap. So you will only see it if you extend too far enough orbital periods. And then the last thing I wanted to show you is the fits to the radius valley as a function of stellar mass here. So we can do fits with the gap fit package to our synthetic planets in the different scenarios. We don't always find a gap, so I only plot those where we found a gap. So this is for the mixed scenario. For the layered scenario, except the lowest stellar mass, where we filled in the gap, right, as I mentioned before. And the sequestration gaps are relatively low here. So the sequestration and layered scenarios are kind of under predicting the location of the gap, while the fully mixed result are over predicting them. So maybe this hints at nature being more complicated and never the end members of the scenarios. So maybe it's not fully mixed, maybe it's not fully layered. This would be I guess it goes in this direction. Probably it's also more complicated anyways. The slope, I'm sorry about the diagram. The values are a bit all over the place, but I think more or less within the uncertainties of the observations, we are in agreement. What I think is important to discuss now is that this interior atmosphere link, which I included in collaboration with the people from Zurich, is really the upper limit to water sequestration. One would also have, at some point, when the planet cools down, crystallization of the mantle, and then much less water can be bound in the rock compared, so it could lead to outgassing. Something we should include. Of course, we should include different volatile species. So the major shortcoming is basically that we excluded hydrogen helium, but we had hydrogen helium as part of the model. So this would be probably the other next thing. And just yesterday on the archive, an interesting paper by Aaron Verlen came out where he started into so for me it's a start to introduce chemistry into the problem. So he has this global chemical equilibrium model of core, mantle, and atmosphere all in equilibrium at the boundaries, and what you then get is also different species. So the water is no longer water, and you similar to the sequestration results, the green points, you put a lot of your so your envelope mass is quite a bit lower than the total budget of your volatile species. So hydrogen, helium, and volatile species. It's only half in the sequestration result, which is in the envelope, and even less often in this chemical equilibrium model. You sequester even more, so which is mainly also the hydrogen which is sequestered. And then if you look at how much the core and mantle includes of just the ice and the refractory species, it's then so yeah, it would usually be half if in this mixed scenario. So the core mantle is the rock, which is about half of the mass in our mixed scenario because the volatiles are all in the envelope, but it's of course correspondingly more massive here. So it's basically the other effect. So more massive cores, less massive envelopes, and a lower mean molecular weight in the atmosphere a little bit. So all these things would affect the evolution, and I think this is the next logical step to take in this interior atmosphere business. And with that, I come to my conclusions that we still think sub-Neptunes can be migrated water-rich worlds, and we should really think more about sequestration. It can have a large effect. The way we did it here with just water did not improve the match to observations compared to the mixed scenario, but I think there's more work to do, and I'm happy to take questions or ideas. Thank you.
Thank you so much, Remo, for this amazing talk. It's really interesting to listen to you. So I would like to open the floor for questions. And please, if you are willing to do this, turn on your video when you're asking questions so that it feels more personal for the speaker. So I already see that there is a question in the audience. So Shanul, please unmute yourself and ask your question.
Hello, can you see my screen and can you hear me?
Yes.
Yes.
Yeah. Thank you. Thank you for your very nice talk. I'm a PhD student of NAUJ. So I have a very naive question about the mix difference between mixed scenario and the sequestration scenario. So what I'm interested in, so I'm thinking I might be biased, but I think that it is very hard to think that if the atmosphere is highly, for example, highly mixed hydrogen and water atmosphere, and if it contains a silicate core, that I cannot imagine that how it cannot react with the atmosphere. So do you have any some possible explanations of that mixed atmosphere without sequestration case might explain the real situation? If that is true, then what would be the mechanism that blocks the reaction between magma and atmosphere?
Yeah, I think you're right. If I understood correctly, you're also hinting at that we have chemical reactions that should take place, right? If I
Yes.
understood. Yes, I agree. So I think this sequestration scenario is more of a first attempt if we only had water, but then yeah, I would really expect reactions to occur and yeah, it's of course make things more complicated. So coming from a formation perspective, that's probably the honest reason why we didn't do it differently yet. So we going step by step and include just staying in this picture of just having water, hydrogen and helium. So it's rock and the cores are still five constituents, but in the future we need to include more. Yes, yeah, I agree. I fully agree.
Thank you. I also have one more question about the submitted version to the archive. So you said that you revised your result for the water sequestration case. And as far as I remember, your submitted archive paper, there's some evolution track of sample cases for different four models. But I found that the sequestration cases, the radius touches the bare rock point and makes a secondary atmosphere after it. So one the question is that whether it is the real result or from your numerical bugs you mentioned here today. I just wanted to ask you.
Yeah, it's going into the details, of course. So the way I developed the code is I first had this idea that I first remove completely the envelope above and then outgas in a second step. That's why I introduced this secondary outgassed envelope after a first thing. And then we thought it's probably more realistic to have this equilibrium. So after each iteration of the code, we check again how much water can be sequestered into core and mantle. Given the lower atmospheric pressure, lower total mass of the planet, it changes a little bit. And so what we expected should happen is that then the core starts to outgas. And then because of just a silly bug in the code, actually we didn't this equilibration wasn't happening. So we always got the result, oh, there's still space, there's still enough space space to store in the core and the envelope. So we actually still, even though we thought we now have the equilibrium model, we actually didn't have that, and we had still the code transition to losing everything from the first and then building up the secondary atmosphere. But now with these results, we have a smooth. It became much more smooth for except some tens or so of very tricky simulations. But for the typical evolution, we now have a smooth transition to this state. So I think it's much better.
Yeah. Thank you for your explanation.
But it's not uploaded yet. I'm sorry. So I probably upload it after acceptance of the paper when everything is clean. Then we have it.
Yeah. Thank you.
Right. Thank you, Harrison. Feel free to ask your question.
Hi. Yeah. Nice talk. I was wondering. So at the start, you talked about these papers which look at the evolution of thermal structure. These MESA papers which focus on, I guess, like gas dwarf scenarios, like the hydrogen-dominated scenarios. And you also mentioned the work by Jonas Haldeman on structure for steam worlds. I was wondering, in your recent modeling with this modeling with the evolution, how exactly you're calculating radius from surface pressure? Like, what are you assuming about atmospheric structure? Yeah, like I haven't read the preprint, so maybe I missed it.
Yeah, there's of course, I didn't go into all details so we do solve the envelope structure, and for us envelope, so I guess that's terminology coming from formation modeling. Envelope is the in this mixed scenario, it's then hydrogen helium with Chabrier equation of state and water with aqua equation of state. But we don't have an equation of state, a true equation of state for the mixture, right? So we have to combine the two equations of state. Some additive with the additive volume law. I forgot the name again, but which is not physically true, but it's a first attempt. That's what one can do. And with this equation of state, one can solve the envelope structure, the thermal evolution, and you also need to assume some opacities. For the opacities, we don't have access to the right mix yet. So we use the Friedman opacities, which are just scaled with Z. But in principle, they assume some other kind of chemical mixture. But maybe if we go to the chemical equilibrium models, maybe we then actually end up with the Friedman chemical mix. So maybe that's actually a step ahead from the rest. But yes, that's how we do the envelope, and the core below is just it doesn't have a resolved structure. It doesn't have a numerical layering. It's just we set some average temperature and then calculate the density. So
thanks. So in the atmosphere, then, do you find that this? I think you're using, is it Gas law? Is additive volume additive mixing law or something like that? Yeah.
Yes.
Do you find that makes a difference then compared to just assuming an ideal gas? Or
yes. So for let's say in the gas dwarf without water, for sub-Neptunes, it might be actually okay to use the ideal gas law. It's not exactly the same, but to higher and higher masses, you have a big difference. So I remember from our formation modeling that if you calculate gas accretion from ideal gas gas giants, you get very different results compared to using an equation of state like that of Chabrier or yeah. So it changes quite a bit. You also change your critical core mass when you go into runaway quite significantly. So yeah.
Thank you.
All right, thank you, Harrison, for the question. Now I see that Kopalan has a question. Go ahead.
Hello, nice talk. Thank you for explaining so many diverse concepts nicely. I had a simple question about the mass distribution that you showed in a situation where there is planetesimal accretion and pebble accretion.
Yeah.
So you said that when there is a pebble accretion, it is more flat, and in case of planetesimal, it's more peaked. So does this also, do you take into account that in the pebble accretion, does it show any excess accretion of volatiles like water or moisture or ice? Does the model take into account, or does the observation show any difference? Is there anything that you can comment on?
So for we both the planetesimal and pebble model here, they
Yeah.
do take into account that you have an excess of material due to the water and the volatiles,
Okay.
a bit in different ways. So it's not the same model. One should, of course, make a fair comparison with one model in
Okay.
principle, all the
Okay.
assumptions the same.
Uh,
But yes, so we have both the Venturini model and ours, which is planetesimal based. We both have an increase of the mass just by the fact that there's also the volatiles condensed out in the solid form. But the
okay.
pebble models have this additional effect via the size of the grains, the stickiness of the grains.
Right. Right.
Or the pebbles. And therefore, this is the main reason why they get an additional mass increase to sub-Neptunes.
I had one
Also, I
more.
think it's linked because pebble accretion is more rapid. So in planetesimal accretion, basically you always start migrating as soon as you have type 1 migration, but pebble accretion can be on timescales shorter than the migration timescales. So you go through on this migration map, you shoot upwards before you start migrating. So that's also part of the story.
Okay. Thank you. Thank you very much.
Actually, I'm going to take this time to ask a quick question myself. So usually in these n-body simulations leading towards planet formation, each planetesimal is kind of assigned a composition, and the final composition of the planet is kind of like the sum of the composition of all the planetesimals that have been accreted. But you might also have some compositional fractionation going on during accretion. Like during collision, you would expect to lose at least some volatiles. But you can also desiccate some bodies through short-lived radiogenic nuclides. Is it something you include in your modeling, or is it something that you think would change these results?
It's a very good question. So it's not included in the modeling yet. So we assume perfect mixing. Like I think that's sadly still the standard in all these n-body interaction. So I know that there's SPH simulations which try to address the fact that you could strip part of your volatiles. In principle, in this picture here, where water is then in the gas phase, it might be even more efficient, right? In stripping the water from the planets. And that's definitely something I'm, at least in that sense, basically doing what we always did and allowing for the gas phase to be lost in the formation stage. So collisions in our case were treated perfect merging of the cores, but for the atmospheres, we assumed the bigger body keeps the atmosphere, the gas, and the smaller body loses it completely. And then for the bigger body, we of course have our internal structure, and then we can have due to the impact luminosity from the so we of course from the n body we have the exact energy of the collision. So we inject that into the planet structure, and then it increases in size and can overflow. So basically by this mechanism, we lost some of the gas due to collisions, but this was always the hydrogen helium only. This is still the case because the formation phase is from 21. And this is a very good point. I should not forget in the next iteration of simulations, one should from in the formation phase mix the envelopes, and then you could also lose water. Yeah. So from in that sense, though, 30% roughly in mass of the water would only reduce and not increase.
And Jenny?
Yeah, just a quick question. Thank you so much for the really cool talk. This is kind of a follow-up from Rob's question, which is in your discussion points, you mentioned, what if the full reservoir of water in the core, etc., isn't taken up? And I was wondering, obviously it's going to be a complicated question, but presumably that could depend on how differentiated the planetesimals are, or pebbles, etc., coming in. And for example, if they weren't, some of them weren't differentiated, maybe that you would have a larger cross section for iron to interact with water, and the bigger cores maybe have less of that surface area. I don't know if that would make a difference, but is it something that is trackable in your formation model or something you're thinking about?
I haven't thought about this yet. I think it's two steps ahead for now. That one. So you're thinking about the chemistry that happens when the matter falls in, or at least the evaporation one should think about. Yeah, and I think there's for pebble accretion, it's very reasonable to believe that the water is lost in the envelope, and who knows what happens for the refractory species in the pebbles, whether they sink to the core as small dust or whether they also evaporated, and that's certainly a possibility. So I think Alona Vazan and Chris Ormo's model go a bit in this direction. So I was thinking a bit along these lines, and for planetesimals it would be a bit similar, but just at higher mass, at higher temperatures, you only sublimate them completely. But for now, we would probably go with something simple, like you put the refractories to the core and volatiles into the envelope is what we will do in the next iteration, probably. But you're right, one should yeah. And then chemical reactions is maybe everything equilibrizes anyway afterwards. Maybe it doesn't matter if the timescale of basically the whole planet equilibrizing is short enough, then it wouldn't affect so much the results.
Thank you.
All right, if there's any final short question. If not, then I think this is a nice time to wrap up. So thank you very much again, Remo. It was a really interesting talk. Really excited to have you here. And thank you everyone for attending. And hopefully see you at the next iteration of the Rocky Worlds discussions.
Thank you very much. Bye-bye.